Somewhere beneath a mountain range in western China, engineers spent over a decade digging through some of the most dangerous rock on the planet. And what they built on the other side is a tunnel so extreme that geologists said it should not have been possible with current technology. Not a simple hole through the soft dirt. A passage carved through rock so unstable that it tried to crush the machines digging it, through underground rivers that flooded the worksite without warning, and through heat so intense that workers had to be rotated out every few minutes just to avoid collapsing. This is not a tunnel built for a subway or a short mountain pass. It stretches for kilometers through some of the harshest geology on Earth, connecting regions that used to require a full day of driving around the mountains just to reach each other. Engineers who worked on similar projects in Europe and Japan have called the conditions inside this tunnel some of the worst ever encountered in modern tunneling history. If you like videos like this, please hit the like button because these take a lot of work to put together, and subscribe so you do not miss the next one. What makes this tunnel so extraordinary is not just its length or its location. It is the sheer number of ways the mountain itself fought back against the engineers trying to dig through it, and the strange, almost desperate solutions they had to invent just to survive long enough to finish the job. A tunnel through the world's most dangerous rock. The tunnel at the center of the story is the Songzhuling Tunnel, part of the Sichuan-Tibet Railway, one of the most ambitious infrastructure projects ever attempted in mountainous terrain. It cuts directly through the Hengduan Mountains, a jagged, unstable range formed by the same tectonic collision that pushed up the Himalayas, meaning the rock inside this mountain range is still actively shifting, cracking, and settling even today. The tunnel stretches for more than 16 kilometers, burrowing straight through peaks that rise thousands of meters above the valley floor, in a region so remote that supplies sometimes had to be brought in by helicopter before proper roads could even be built to the worksite. To put the difficulty in perspective, most tunnels are dug through rock that behaves in a fairly predictable way, hard enough to hold its shape once cut, stable enough that a tunnel boring machine can grind forward at a steady pace for months at a time. The rock inside the Hengduan Mountains does almost the opposite. It shifts underfoot without warning. It fractures in ways that do not follow any consistent pattern. And in some sections, it behaves less like solid stone and more like a slow-moving liquid, a phenomenon engineers call squeezing ground, where rock under enormous pressure deep underground actually flows inward around a tunnel over time, slowly crushing anything left inside the space if it is not immediately reinforced. Add to that scalding underground hot springs, sudden pockets of high-pressure water, and rock temperatures inside the tunnel that have been measured at levels close to 90 degrees Celsius in certain sections. And you start to understand why engineers on this project have described it as digging through one of the most hostile environments on the planet. Not because of anything visible on the surface, but because of what the mountain itself is doing deep underground. Why ordinary tunneling methods fell apart here? Modern tunnel construction usually relies on one of two basic approaches. The first uses a tunnel boring machine, an enormous rotating cutting head that grinds continuously through rock, moving forward steadily while installing support rings behind it as it advances. A method that works incredibly well in consistent, predictable rock conditions. The second relies on a drill and blast method, where engineers carefully place explosives to break apart harder or more irregular rock sections, then clear the debris and reinforce the tunnel before moving forward. Both methods depend on one basic assumption, that once you dig a hole, the surrounding rock will generally stay where you left it, at least long enough to install support before the space is sealed off. The Hengduan Mountains broke that assumption again and again. Sections of squeezing ground meant that tunnel walls carved out 1 week could visibly deform and narrow within days, the surrounding rock slowly pressing inward with enough force to bend steel support rings that would normally hold their shape for years in a typical tunnel. In some sections, engineers reported watching support structures crumple under pressure that built up faster than anyone anticipated, forcing crews to reinforce and even completely rebuild finished sections of tunnel that should have already been stable. Then there was the water. Unlike a predictable underground river that engineers can map and plan around, this mountain range is riddled with pressurized water pockets that can burst without warning. The moment a drill or blast disturbs the surrounding rock, sending scalding hot water rushing into the tunnel at pressure high enough to injure workers and destroy equipment in seconds. Several sections of the project encountered what engineers call water inrush events. Sudden floods of water and mud bursting into the tunnel from fractures in the rock, some carrying so much force that entire work sections had to be evacuated and sealed off. Before crews could even assess the damage. Heat became its own separate battle. As the tunnel pushed deeper into the mountain, rock temperatures in certain stretches climbed high enough that standard construction equipment began to fail, electronics overheating, cooling systems struggling to keep machinery functional. And human workers facing genuine heat exhaustion risks in an environment where the surrounding rock itself was radiating heat like an oven. Traditional tunneling schedules, built around a steady, predictable pace of digging, simply could not survive contact with a mountain that kept changing the rules every few hundred meters, fighting rock that moves like liquid. To handle the squeezing ground problem, engineers developed a technique that essentially treats the tunnel less like a fixed hole, and more like a structure designed to flex and absorb pressure without breaking. Similar in concept to how modern earthquake-resistant buildings are designed to sway and bend, rather than rigidly resist force and eventually crack. Instead of installing completely rigid steel supports that fight directly against the crushing pressure of the surrounding rock, certain sections use specially designed support systems that can compress slightly under load, absorbing some of the mountain's pressure, rather than transferring all of that force directly into a brittle structure that would eventually shatter. Think of the difference between bracing a door with a solid steel bar versus bracing it with a heavy-duty spring-loaded system. The solid bar holds firm until the force against it becomes too great, then it snaps or bends catastrophically all at once. The spring-loaded system gives a little underpressure, absorbing the force gradually instead of resisting it completely until failure. Certain sections of this tunnel use a similar philosophy, support structures engineered to yield slightly and redistribute pressure rather than rigidly resisting a mountain that refuses to sit still. Engineers also relied heavily on real-time monitoring systems, sensors embedded directly into the tunnel walls that continuously track even tiny amounts of rock movement, pressure buildup, and temperature change, feeding that data back to engineering teams who can adjust reinforcement plans before a section becomes dangerous rather than after. This turned tunneling through this mountain range into something closer to a constant, evolving negotiation with the rock itself, rather than a fixed plan followed from start to finish. Taming water that explodes out of solid rock. Dealing with sudden pressurized water pockets required a completely different strategy, one built around detecting danger before it strikes, rather than reacting after the fact. Engineering teams used advanced geological scanning technology, essentially a form of underground radar, to probe the rock ahead of the active tunnel face before drilling or blasting in that area, searching for signs of hidden water pockets or unstable fracture zones before crews ever got close enough to trigger a sudden inrush. When a potential water pocket was detected ahead of the tunnel, crews would drill small pilot holes first, deliberately releasing water in a slow, controlled way, rather than allowing pressure to build up until it burst violently all at once. It is a similar idea to slowly releasing pressure from a shaken soda bottle by cracking the cap open gradually instead of popping it off all at once and getting sprayed. By finding and draining these pressurized pockets carefully in advance, engineers turned what could have been a catastrophic, unpredictable flood into a controlled, manageable process. Where water inrush events still occurred despite these precautions, specialized pumping systems capable of moving enormous volumes of water extremely quickly were kept on standby throughout the project, ready to be deployed the moment a section flooded, buying crews critical time to evacuate safely and assess the damage before deciding how to proceed. This combination of predictive scanning and rapid emergency response became the backbone of how crews survived a mountain that seemed determined to flood them out at every opportunity, cooling a tunnel that behaves like an oven. The extreme underground heat required its own dedicated engineering solution, essentially building a portable climate control system that could function deep inside solid rock, far from any normal ventilation source. Massive industrial ventilation systems were installed to constantly pump fresh, cooler air deep into the active work zones, while equally powerful extraction systems pulled hot, stale air back out, creating a continuous flow that kept the immediate work area survivable, even as surrounding rock temperatures climbed toward levels that would otherwise be dangerous for both workers and machinery. In the hottest sections, crews adopted strict rotation schedules, limiting how long any individual worker could remain in the most extreme heat zones before being swapped out, treating heat exposure with the same seriousness as a hazardous chemical environment, rather than simply pushing through discomfort. Equipment designed for standard tunneling conditions had to be specially modified with additional cooling systems, just to keep electronics and hydraulics from failing under sustained high temperatures. Essentially retrofitting standard construction machinery to survive conditions closer to what you would expect from equipment designed for desert oil fields, rather than a typical mountain tunnel project. Why China pushed through a mountain that fought back this hard? The obvious question is why anyone would attempt a project this dangerous and difficult in the first place. And the answer comes down to the same logic behind China's high-speed rail expansion to some of its most remote regions. The area connected by this tunnel has historically been isolated by exactly the kind of terrain that made digging through it so brutal, mountains so steep and unstable that building roads around them required long, winding routes that could take an entire day to travel a distance that would take under an hour in a straight line. That isolation has kept entire regions economically cut off from the rapid growth happening in China's major cities, with agricultural goods, patients needing medical care, and students trying to reach better schools all facing the same brutal mountain geography as an obstacle. A rail tunnel through this range does not just save travel time, it fundamentally reconnects communities that have been separated by geography for their entire history. Once complete, the broader railway line this tunnel is part of is expected to cut travel time between major regional hubs from what used to be a multi-day journey down to just a few hours, opening remote mountain communities to trade, tourism, and access to services that were previously nearly impossible to reach reliably. There is also a broader strategic dimension to projects like this. Successfully building infrastructure through some of the most geologically hostile terrain on Earth gives Chinese engineering firms and construction companies a level of expertise that very few other countries in the world currently possess. Expertise that can then be exported to other nations facing similarly difficult mountainous terrain, whether in Central Asia, South America, or parts of Africa. Every brutal lesson learned fighting squeezing rock, flooding water pockets, and extreme underground heat becomes a competitive advantage the next time a similarly difficult project appears anywhere else on the planet. The limits and the cost of pushing this far. It would be dishonest to present this tunnel as a simple triumph without acknowledging the real cost involved. Projects through terrain this hazardous come with construction timelines stretched far beyond initial estimates, budgets that balloon well past original projections, and in the most difficult mountain tunneling projects in China's history, worker safety incidents that serve as a sober reminder of just how dangerous this kind of environment truly is, even with modern engineering and safety protocols in place. This is not a technology that can simply be copied cheaply or quickly anywhere else in the world. It requires years of specialized geological survey work, enormous financial investment, and a willingness to accept schedule delays measured in years rather than months when the mountain refuses to cooperate. Nor does every mountain range demand this level of extreme engineering. Most tunneling projects around the world still occur through far more stable, predictable rock, where standard tunnel boring machines and conventional support systems work perfectly well, without needing any of the extreme measures developed for this specific project. This tunnel represents the far edge of what is currently possible, not a new baseline expectation for ordinary tunnel construction everywhere. But the techniques proven here, flexible support systems that absorb pressure instead of rigidly resisting it, predictive scanning that detects hidden water pockets before they burst, and industrial-scale cooling systems that make extreme underground heat survivable, are already influencing how engineers approach other difficult mountain crossings around the world. What once seemed like an impossible tunnel through rock, actively trying to destroy the machines digging it, has instead become a working blueprint for pushing into terrain that engineers everywhere else have simply avoided for generations. Somewhere beneath those same mountains today, trains are running through a passage that took over a decade of fighting collapsing rock, flooding water, and oven-like heat just to exist, carrying passengers through in a fraction of the time it once took to drive around, most of them completely unaware of just how close that mountain came to winning. If this story about the tunnel dug through some of the most dangerous rock on Earth surprised you, hit the like button, subscribe, and turn on notifications so you never miss the next one. There are more videos on the screen right now if you want to keep exploring. So, here's my question for you. After hearing what engineers had to survive to build this, would you ride a train through a tunnel like this one? Or does digging through rock that behaves like a living, moving thing make you want to take the long way around? Let me know in the comments below.